Welcome to example number 7. In this case, we have a car that is traveling at 23 meters per second and then slams on its brakes, locking its wheels. We're given the coefficient of friction, and we're asked to find out how far the car would skid before it comes to a halt. So let me first draw a little picture to kind of help you understand what's happening. So let's say this is the car before, and it is traveling at, whoops, 23 meters per second. So we'll put that v sub 0 at 23 meters per second. And then it finally comes to a halt. So the final speed is 0 meters per second. So this is our after picture. Of course, there's friction along here. And let's go ahead again with our energy bar graph modeling approach. And there we go. Some of our students like to call these the LOL diagrams. We have energy here. And then let's decide what our system's going to be. It'll be the car, the earth, okay, I guess in the ground as well, I suppose, which is kind of like the earth. And we have kinetic energy, we have gravitational energy, we have, well, there's not any springs, I won't include that in there. So we have kinetic energy, gravitational energy, and maybe some other energy like, I don't know, dissipated here. Okay, so go ahead and put down what you think would be the bar graph situation for the before situation and then afterwards. To make life easy, I'm going to assume that this reference level right here is y equals 0. That means that I won't have any gravitational energy. So we have no gravitational energy throughout the problem. The car is not going uphill or downhill, just going along a level hill. So we really only have kinetic energy at the beginning, which basically gets dissipated outside. But let's say we decide to not include the ground, and the ground is on the outside there. Then we could look at it as work being done. And you could say that this is just simply work. So the energy before, which is basically kinetic energy, is basically lost out of the system and turned into work done by friction. So that would be dissipated energy outside of the system. So this work is actually going to put a little subscript F to represent the work done by the friction force. All right, so if we were to calculate the kinetic energy or the energy of the system before, it would be just kinetic energy, and that would be 1/2 V initial squared. By the way, I have no kinetic energy at the end because it's not moving, and we've assumed the gravitational energy remains constant. All right, and so then we have that, we can find the work done by friction, which is equal to 1/2 mv squared. And we could calculate that, I suppose. We could go 1/2 mass is 1,800 kilograms. I guess I should write down my known. There's our all known information. So 1,800 times our speed of 23 squared. So then we could figure out the work done as the energy dissipates outside of that system. That work done would be equal to 476,100 joules of energy dissipated out of the system. But we're not asked to find the work done by friction. In part A, our unknown that we're looking for is actually the displacement d. If you recall, the work is equal to the change in energy. And that change in energy is basically kinetic energy. So it's equal to the kinetic energy, which I just found out, right? But what's the definition for work? Well, it's that force, the parallel force, multiplied by the distance d. And that parallel force, if you think about that car here, and we were to draw a free body diagram for the car, we have the normal force, the force of gravity, which are equal and opposite to each other. But the force that's actually doing work on the car, making it slow down, is this backward force called friction. This is what's causing the car to slow down. This is the negative acceleration that it's experiencing. So the force that is parallel to the direction of the movement is actually the force of friction. So Ff is really that parallel component of that force multiplied by the distance equals the kinetic energy. You can put the number in here if you want for kinetic energy, but you know what? I'm just going to go ahead and put the equation in here because you're going to see something happening with a cancellation possibly. Okay, so we need to find out that force of friction, and hopefully you recall. You see, you're given a coefficient of friction. so it must be using that somewhere, the force of friction is equal to mu sub k times the normal force, where the normal force is equivalent to the force of gravity because the sum of the forces in the y are equal to 0. And the normal force would be equal to Fg, and Fg is equal to mg. So we could replace the normal force with mg. So now we know the coefficient of friction times mg is equal to the force of friction. So let's sub that in over here. We have mu sub k times m times g times d equals 1/2 mv0 squared. And the reason why I didn't go with this number over here is because I could actually solve this problem without really needing to know what? The mass of the car. Why do I not need to know the mass of the car? Because it cancels. So it's going to be the same answer here, regardless of the mass of the car. So let's rearrange for d. D would be equal to v sub 0 squared. 2 is on the denominator. So 2 times mu sub k times g. So the distance that it skids is directly proportional to the square of the velocity. That's a very important thing to realize. D is directly proportional to the speed squared. It means if you double the speed, there's going to be a squared factor on here. That means the kinetic energy is going to be quadrupled, and that means you're going to need 4 times the stopping distance to stop. It's a very common question on driver license tests, by the way. So we now can substitute our numbers in. So D equals V0 squared is 23 meters per second squared times 2, and coefficient of friction is 0.7, and G is 9.8. And the distance will come out to be 38.55, let's say 6 meters. Okay, let's go on to part B, and I really don't have much room here. Let's just put it down over here. So, how far would the car travel if it was going twice as fast? So now if V0 primed is equal to 2 times 23 meters per second, which is basically 46 meters per second. So, I mean, what you could do is just simply put it back all into here and solve for it. But you know what? You don't really need to. If you look back at this relationship I talked about here, the distance, we just proven, the distance that it skids is directly proportional to the speed squared. That means that if you multiply this speed by 2, and you know that's being squared, whatever happens to the right side of the equation must happen to the left side of the equation. So that's directly proportional to the distance. So the right side is being multiplied by a factor of 4, then the left side of the equation must multiply by a factor of 4. So the distance, the new distance that's going to skid, is simply 4 times my original distance. That's 4 times 38.6 meters. And it gives you a distance, skid mark distance of 154 meters. And part C, I kind of answered earlier when we went back to the energy bar graph. Originally when I didn't include this as work, and I considered the ground as part of the system. And in that particular case, really this energy here is essentially dissipated now. Well, what kind of energy is it mostly dissipated as? It's mostly thermal energy. If you feel the ground and the tires afterwards, you're going to notice it's a lot warmer. So I would say that energy that it had, that kinetic energy, is converted or transformed into a dissipated energy, which is mainly thermal energy. And that's it for this example.